Good morning, grade 9. Hope you are all doing well and being safe. This is Miss Pamela Tini giving the physics course. Today we are going to continue section 2 in chapter 6, which talks about work and energy. So please open up your books on page 202 and follow up with me. In the previous session, we talked about kinetic energy. Today we are going to talk about potential energy. Let's imagine a situation where we must lift a bowling ball and put it on a shelf. You must do work if you want to lift a bowling ball from the floor onto a shelf. Of course, because you are moving the ball from one location to another. Once on the shelf, the bowling ball has zero kinetic energy. Why? Because it is not moving, and kinetic energy is the energy of an object in motion, just as it did on the floor. Even so, the work you did in lifting the ball has not been lost. It is stored as what? As potential energy. If the ball later falls from the shelf, gravity will do the same amount of work on the way down as you did in lifting the ball up. So let's say you did an amount of 80 joules of work in order to lift the bowling ball and put it on the shelf. When the ball falls from the shelf, gravity will do also an amount of 80 joules of work in order to get the ball back on the ground. As a result, the work you did is recovered in the form of kinetic energy. You can see this example in figure 6.6, page 202. Energy that is stored for later use is referred to as potential energy, or PE. So this is the definition of potential energy. You can think of potential energy as a storage system for energy. So it is a system that stores energy. When we increase the separation between the ball and the floor, so when we increase the amount of work that we exert on the ball in order to lift it up, the work we do is stored in the form of increased potential energy. So if I lift the ball to a height of 2 meters, it will have more potential energy, more stored energy, than when I lift the ball, let's say 0.5 meters. Potential energy has several forms. One of the most common is called gravitational potential energy. The potential energy of an object is determined by the amount of work required to move this object from one location to another, as we already stated in the previous example. So in the case of gravity, the work is mgh, and this work is stored as gravitational potential energy, PE, gravity. So in order to calculate gravitational potential energy, we use the equation that we see in front of us. PE gravity is equal m times g times h, where PE gravity is gravitational potential energy measured in joules, m is mass measured in kilograms, g is acceleration due to gravity measured in meter per second squared, and it is equal to 9.81 meter per second squared unless it is stated otherwise, and h is the height of the object measured in meters. By rearrangement of this equation, we can calculate the mass of an object if we know its gravitational potential energy and height. Using the first equation, mass is equal to gravitational potential energy over acceleration due to gravity times height. And we can also calculate the height of an object if we know its mass and potential energy, gravitational potential energy, using the second equation. Height is equal to gravitational potential energy over mass times acceleration due to gravity. Example. Find the gravitational potential energy of a 65 kilogram person sitting on a diving board that is 3 meters high. Here we must be careful. If the mass is given in grams, we divide it by 1000 in order to convert it to kilograms. And if the height is given in centimeters, for example, we divide it by 100. If it is given in kilometers, we multiply it by 1000. So the units must be kilogram and meters in order to get the equation right. So gravitational potential energy is equal to mass times acceleration due to gravity times height, which is here equal to 65 kilogram times 9.81 meter per second squared times 3 meters, and the final answer is 1900 joules. Now the second kind of potential energy, which is elastic potential energy. Elastic potential energy is potential energy stored as a result of deformation of an elastic object, such as the stretching of a spring. It is equal to the work done to stretch the spring, which depends upon the spring constant K, as well as the distance stretched, as you can see in the figure in front of you. This is a spring that is stretched a distance x. So, The elastic potential energy stored inside the spring due to its stretching or its deformation is equal to the work done to stretch this spring. In order to calculate the potential energy of a spring, we use the equation we see in front of us. Potential energy of a spring is equal to half times K times x squared. Where potential energy in a spring is measured in joules, K is the spring constant measured in newtons per meters, and we talked about it once when we took Hooke's law, and x is the stretch or compression distance of the spring measured in meters. So if it is given in centimeters or in kilometers, we convert it and then we calculate. By rearrangement of this equation, we can find the stretch or compression distance of a spring using the first equation you see in front of you. X is equal to radical 2 times potential energy in a spring over spring's constant. And we can also know the spring's constant if we know its potential energy and its stretch or compression distance using the equation we see in front of us. K is equal to 2 times potential energy in a spring over x squared. Now, as an example, we are going to solve example 6.12 on page 205. So please open up your books and concentrate with me. A spring with a spring constant of 120 newtons per meters is compressed a distance of 2.3 centimeters. How much potential energy is stored in the spring? So here we need to find the potential energy of a spring. The given is K equals 120 newtons per meter and X is equal to 2.3 centimeters. Of course, we change it into meters by dividing it by 100. So it is equal to 0.023 meters. In order to find the potential energy of a spring, we use the equation half times K times X squared. So half times 120 times 0.023 meters squared, and it is equal to 0.032 joules. So the spring has a potential energy of 0.032 joules when it is compressed a distance of 2.3 centimeters. As a homework, please solve numbers 23 and 24, page 204, and numbers 25 and 26, page 205. Your homeworks must be done and submitted to me on Tuesday, May 19. Thank you, good luck, and stay safe.